So, just some additional probability practice. Number 4 was one of those where you have to figure out what's given and what's not. And so the idea, so there was some information, it was like, it's too thick. There was like, it was like 17.9% of households, are in the Northeast. That's what the problem said. Said that 19.8% of households earn $100,000 or more, and then it said of those in the Northeast, then 5.4% earn 100,000 plus. All right. So then the question is, and then my question was, I don't even remember, calculate probability that the household is in the Northeast and they earn $100,000 or more per year. That was the goal. So the and probability, we know typically that involves multiplication. In this case, we don't have the sample space, so we can't really use like counting tricks or like going back to the sample space. We're going to just have to use those probabilities somehow. And you got to go back and figure out, well, I'm going to multiply two probabilities because it's an and probability. I don't really know which two I should multiply together, and it depends on what the given condition is. One of those probabilities is conditional, the other two are not. And so normally I'll give names. So like we'll call, let's say N is the event that the household is in the Northeast. And let's say E is the event that they earn 100,000 plus. And then, so what you have here, so then this right here, 17.9%, this is the probability of being in the Northeast. This one is the probability of E. Now, this one right here, this is this is a given condition. So this right here is telling us what the given condition is. This is telling us that it's given that they're in the Northeast. That's what that statement tells us. And so then this would be given Northeast. 5.4% is a probability of their earnings. It's not about being in the Northeast. So it's the probability they earn that much given they're in the Northeast. And so then when we go to calculate this probability, so the probability that they're in the Northeast and they earn $100,000 or more, well, if you go back to the general multiplication rule, the general multiplication rule says it could be two ways. So it could be P of N times P of E given N, right, because the given condition has to match the first probability, or it could be the probability of E times the probability of N given E. And either one of those formulas will work, but we only have enough information to use it one way, because we have the probability that they earn 100,000 given that they're in the Northeast. That's this one. That's this one. We don't have the other condition, or probability. We don't have the probability that they're in the Northeast given that they earn. And so in this case, this one right here, we don't know. It's not given to us. And so that means that we can't use the probability of E. It's that probability of E is extraneous. And so here we'll use the probability of N and then the probability of E given N. And so it's going to be the product of those two probabilities. And that'll be the solution. I don't know what that comes out to be.
0096.
0.0096? Is that right? Is that too many zeros? Or is that right? That sounds reasonable. I trust you. Anybody else get that number? I just want to confirm. Cool. Yep. I got 00918.
Yeah.
But either way, it's pretty close. Something like that. If you're going to round to 4 decimal places, that's typically what I do just for fun, but it'd be something like that. So Okay. So and probabilities, the key, you can pretty much usually and probabilities are going to involve multiplication. Or probabilities usually involve addition, and probabilities usually involve multiplication. So you can kind of, it's like if you're not entirely sure what to do, you could see this and say, okay, well, it's an and probability, so there's no or probability involved here, right? It's all just probabilities, and then I'm calculating and so I can know that I'm going to multiply, and so, if you could just pick two probabilities and multiply them, and then you got a 1 in 3 chance of getting it right. But so if nothing else, you could just multiply two values together. And
What is the probability
but
that you get this probability?
yeah, I think it would be 1 in 3. Well, that's assuming if you recognize it as an and probability, and you're going to have to multiply two of those 3 probabilities, then that would mean there's a 1 in 3 chance that you get it right. Because if you just randomly select 2 probabilities and multiply them. But
so of those, let's just go into given probability.
yeah, the hard part. Yeah, so that's really what it comes down to. It's recognizing that it's an and probability, so you have to multiply. But once you know that you have to multiply 2 probabilities, you have to figure out which probabilities should you use, and it comes down to figuring out what the given condition is. And since the given condition is in being in the northeast, then we should multiply by being in the northeast probability. That's the key, because the rule says you use one of those 2 forms. So, yeah, those ones are tough. Yeah, those ones are tough. Any other ones on there that you were particularly curious about? Was 4 the one that gave people the most trouble?
I had it right.
You said 3.
Yeah.
That's right. So 3, on that practice one, it was 150 students, okay, and it said that 102 of them, they drive themselves to school at least once a week. It said 64 of them carpool at least once per week, and then it said that 55 of them do both at least once a week. So like one day they drive themselves and another day they carpool, at least once a week. Okay, so that was the setup. And then my question is, what is the probability that a student either drives themselves or they carpool? Right. So in an or probability, we know that or probabilities, they generally involve addition. So I know that I'm going to add some stuff up. But what's the thing about or probabilities?
It's one or the other.
Yeah, and it matters whether or not they have overlap, right? And so, the probability that someone drives or they carpool, so we could think of this as like probability to drive, we'll call it D or C. And so the general addition rule says that you can take the probability of D and add the probability of carpooling, but then you have to make sure that if there's any overlap, you have to subtract out the overlap once because you're going to double count them in both groups. So from here, it's like the probability that they drive themselves, there was 102 out of 150 of those, right? And the probability that they carpool, there were 64 out of 150 of those, but then there was that overlap because 55 of them did both. And so the 55 are in both groups. So the 55 are in the 102 and the 55 are in the 64. And so they get double counted, so we subtract them out once. And so 102 plus 64 was at 166 minus 55 is 111 out of 150. And then whatever that comes out, if you approximate that to, let's say 4 decimals, what's it come out to be? Does it even need to be approximated?
74.
0.74 even?
Yeah.
Yeah. I didn't know if that one would need rounded or not, but it'd be like that. Yeah. So I did post this worksheet in the exam 2 module. I have to put the solutions up, though. I don't have the solutions up to this one yet because I changed it from last quarter to this quarter. But I'll get them up. So
So way more here.
yeah, that's interesting. Yeah, we got all sorts of like pipes and stuff that run up above our ceilings from all the labs and stuff in this building.
I have
Yeah.
a question.
And there's catwalks too, so sometimes people bounce around down there. It sounds kind of like Jurassic Park. It's pretty cool. Anyways, yeah, or they're just messing with us. Yeah. All right. Anything else on there from those practice ones that you particularly want to take a look at? Yeah.
You do the 5B.
5. Yeah. It was the ones. It's kind of like the jury problem, but that one's a little tricky.
I used the Coke and lemonade one for that one.
Yeah.
Yeah.
That one's and that one you have to. So the thing was, so about that one. So the idea was that there was 5 faculty, 7 admin, and 3 students on this this group or this committee. And what they want to do is they want to do a subcommittee. So A and B have to be treated a little bit differently. So the idea is they wanted to make a committee that had 2 faculty and 1 admin and 2 students. That was the idea, right? And the question there was, it wasn't a probability question, it was just a counting question. So how many ways could you have done this committee? And that's a counting problem, like the Coke and lemonade one. This one's a little more straightforward because, there's 5 faculty, and you want 2 of them. That should be a C, not a 2, right? And then there's 7 admin, and you want 1 of those. And there's 3 students, and you are going to pick 2 of them. And you're just going to multiply them all together. So, 5C2 is, I don't actually know what that comes out to
And
be.
should be 210.
Yeah. Yeah, because is that 10 right there? 5C2 is 10? Or is it?
That's 10.
Is it? Yeah, this is 10, this is 7, and this is 3? Oh, yeah, because it's just the number of ways you can leave one person out. Yeah, so it's 210 ways. Okay. That one's not as tricky. B is a little trickier. You just have to reframe the way you look at it. So in B it said, okay, well, let's suppose that you just randomly select 5 people. And my question is, what's the probability that you end up with at least 1 student? Yeah, so if you think back to the the defective TV example, at least 1 is a lot of different events put together because there could be 1 or 2 or 3 or 4. Well, no, there can only be up to 3 students because there's only 3. So it could be 1 student or 2 students or 3 students. So the number of students on the committee, there could be none or 1 or 2 or 3 because that's how many students there are. And so this is the event, say if that's like A, at least 1, this is actually what we're interested in. But what happens is if you're going to calculate probabilities that way, you'd have to calculate the probability of 1 and the probability of 2 and the probability of 3, and then you'd have to add them up using the Coke lemonade kind of strategy. So you'd be calculating 3 separate probabilities and adding them up.
Yeah, I just did it for 1.
Yeah, so that's common. A lot of people will just calculate the probability of exactly 1. And that's different than at least 1, right?
Yeah.
And so that's why in a case where you're doing at least 1, it's actually easier to just do the complement, which is 0. So the probability that at least 1 student is picked, that's going to be 1 minus the probability of 0 students being picked. Okay, and then you can treat this problem like the defective TVs if you reframe it and think about this as 3 students and 5 faculty and 7 admin together make 12 non-students.
30, 12, 5.
Yeah, and so exactly, and so these then when you're going to go calculate that probability. Is in blue, I guess, so I'll stick with blue. So we'll treat this like the defective TV. So there's still, 15 people, and we're going to pick 5 of them, right? That's That's the overall on the bottom. 15 people to pick from. I got to pick 5 of them for my committee. But in this case, I have 3 students. The complement would be, the 0. And then that means the other 5 have to come from those 12 non-students. And then, so you'd actually calculate the probability of 0 students and then do 1 minus that. And I don't know what that number comes out to be off the top of my head. Does anybody have that or remember what it came out to be? I'm not sure what it came out to be. What is 12C5? Any takers?
I'm getting it. It's 0.26373.
2637?
Yeah.
2637 for the whole probability?
Yeah, the whole probability. And so then the answer
Does that sound familiar to anybody else?
should be 0.7362 or 63.
26? Yeah. You got the same thing? Like that. So that's the probability of 0. And then you just do 1 minus that. 6, 3, something like that. Should be somewhere in that vicinity. So. Yeah. You can do it 2 ways. I mean, you can plug all this in your calculator at once. You can just do the combination times the combination divided by that combination. Or you can get a separate one. So you can go 3C0 in your calculator, that's 1. You can go 12C5 in your calculator, some big number. You go 15C5 in your calculator, some big number. And then you just divide the 2 numbers. You should be able to come up with something like that. Anybody get something different? Or other people get something the same? Okay, cool. All right. That one's a little tricky. And the tricky thing, well, there's 2 tricky things about that one. The first thing is that you have to recognize that we're asking at least 1. And anytime you see like at least 1, almost guaranteed it's going to be easier to do the complement, so 1 minus the probability of 0. And then the other hard part about that one is recognizing that to frame this one the way we did our other problems, we have to just think of them as students and non-students. And we need to combine the faculty and admin into one category so that we can do it that way. So, all right. Okay. Probability is a blast. All right. Any other questions from like quizzes stuff or anything else that we've been working on? The quiz is tough. Yeah, it's not the easiest thing in the world. Probability is just hard. It's not like, but I don't want to like focus too much on it because it's not like, it's something we have to cover and talk about just so we understand probabilities going forward, but it's not like the main point of the course. So, yeah. And the stuff before this with like the lines and the regression, I think that stuff is easier, and the stuff after this is easier. It all gets easier. It only gets easier from here. Yeah.
The test on Thursday is mostly going to be this week?
Well, it's 3 modules. It's the regression stuff we did, like the scatter plots and the lines and prediction. Then we got the probability stuff, and now there's just a little bit from module 5 that we're going to cover like today and tomorrow. But it's not a lot of stuff in module 5. It's pretty straightforward stuff. It's a lot easier. Yeah. So
for that 3C0,
yeah.
wouldn't it be like 3-1 and then 3-2 and then 3-3?
Only if you're going to do it the hard way. See, so that's the thing. You could do that. You could do it that way. So, like, if you want to, so there's an easy way and a hard way here. See, so if we think about, sorry, I shouldn't have put a 0 there. If you think about the number, oh, I'm still in eraser mode. If you think about the number of students that you're going to pick for your committee, right? So there's 3 students and 12 non-students. Yeah? Okay, so if you randomly select 5 people, you might end up with no students. You might end up with 1 student. You might end up with 2 students, and you might end up with 3 students. Okay? Now, you could use our trick to calculate all of them. So the one we were just doing, it looked like this. And what would it have to have been? It was 12C5 over 15C5. That would be, like if we're talking about probabilities in this category, that would be the probability of 0. And you're right. You could get the other ones using the pattern. I'll make this table a little bigger so I got room. So if you wanted to calculate exactly 1, like you were talking about, that would be, 3 students, I want 1 of them. 12 non-students, I'll have to have 4 of them because I have 15 people and I want 5 of them. And that'll give you that probability. And if you wanted 2 students, you could get that. It'd be 3C2, 12C, then there'd have to be 3 non-students because ultimately I have 15 people and I'm picking 5 of them. And you could do 3 because that would be 3C3, which would mean we'd have to get 2 non-students because we're still picking 15C5. So you could calculate, so these will all give you probabilities. We calculated this one. It was 0.23, what was it? Or was it 2637? I can't remember what.
2637.
2637, right? And so you could calculate all of these. So you're right. And so now what were we interested in?
At least 1.
We were interested in at least 1. Okay, so that's any of these 3 would satisfy that. So you could, like you were saying, swap out this. You could swap out these numbers, right? 0, 1, 2, 3, and you could calculate the separate probabilities. So you could get a probability here, here, and here. But then what you'd have to do is you'd have to add those 3 probabilities up.
And that'll equal that number up there?
It won't. It'll be the complement. So what we did is since we were trying to do probability at least 1, we said, well, rather than calculating 3 probabilities and adding them all up, why don't we just calculate the 1 probability that isn't what we want, which we got as 0.2637, and that came out to 0.7363. Okay, and if you calculated these 3 separately, boom, 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 and then you added those 3 up, you would get that number. So you don't have to do it with the complement. It's just less work. Yeah. But what a lot of people will do is a lot of people will just calculate this one, and they'll just give me. But that's not the answer. That's the probability of exactly 1 student, not at least 1. Because exactly 1 is different than at least 1. Because at least 1 is a lot of different options.
So if we see that at least 1, we know to do it.
Yeah, if you see, anytime you're trying to calculate like the probability of at least 1 thing, it's usually going to be faster just to do 1 minus the probability of 0. Because there's only 1 event that doesn't satisfy at least 1. Okay? It's like the birthday problem, which we have a lot of people in here, I wonder. But it's easier to figure out the probability that we don't share a birthday than it is the probability to figure out that at least 2 do. So. Okay. All right. Any other general questions? Quiz question? Is the quiz due today, or was it due last week?
It's 12.
This week?
Yeah, it was 2 days, I think, the quiz.
The probability one though was.
Oh, it probably was. That's already
That one was due, right? Yeah. But the 5, the discrete stuff is due. But this section is a little easier, I think you'll find. Okay. So does anybody have any general questions or overall stuff before I move to some new, more applicable, sort of not as nasty stuff? Yeah. Okay. So in the now that we understand kind of how probabilities work, and we have this understanding that things can be dictated by probabilities, and things. Probabilities can be higher or lower. They're always between 0 and 1. And things that have higher probability are more likely to happen, lower probability, less likely to happen. And probability is like a long-run phenomenon. So it's like you're not necessarily going to get 50-50 heads, tails when you flip the coin 10 times. But if you flip it 10 million times, that proportion is going to be pretty darn close to 50%. So what we start to look at then is we start to look at, okay, well, when you are going to go out and you're going to sample a population, then when you draw a sample, you're only looking at a subset of that sample. And you're not necessarily, like if I just randomly picked one of you and asked you, like, how long did it take you to get to school today, right? Well, you could all tell me a lot of different numbers, but some numbers are more likely than others. Like, it's very unlikely that any of you are going to tell me like 0 minutes or 2 minutes. And it's very unlikely that any of you are going to tell me like 105 minutes. 20 minutes might be pretty likely, 25, somewhere, right? Some numbers are more likely than others. And so like when I'm thinking about sampling people and asking them some number about themselves, we would consider that a random variable. So this isn't really a recall. This is actually, I don't know why I put recall in here because I don't think we've actually defined it up to now. It should just say random variable. But this is what it is. So a random variable is a variable whose outcomes are determined by probability. Okay. So what is a variable? A random variable is determined by probability, but what's a variable in and of itself?
Something different than that.
Yes, that's variability. But like in math, what's a variable? Usually we use letters, right? Like X, Y. They're like placeholders for numbers, right? And so in statistics, same idea. A variable, it's a value whose outcome is unknown in advance. Right? So like if you look at the sorry, it doesn't look like English, but it's a value whose outcome is unknown in advance. Like a variable in an equation, it's a number that just holds the place value, the place for an actual number. Like eventually you could fill it in or solve for it, or you could drop a number in there, but you're just holding its place. Variables are the same way. Like if I'm going to observe how long it took you to get to school today, I don't know in advance what you're going to tell me, but I know you're going to give me a number between like 0 and 100 probably in terms of minutes or something. So if it's a random variable, then there's some sort of probability that would dictate outcomes that are more or less likely, though. Okay. Okay, and we're going to focus first here on discrete random variables. And so just a reminder about what is discrete, right? Discrete values, those are things that are what? What does discrete mean? Yeah, things you can have like whole values of, right? So discrete random variables, these are things like, number of siblings. That's one we'll look at in a second. Or, I don't know. Yeah, like number of days worked or something. They're things that you would only report like none or 1 or 2 or 7 of or something like that. Okay. So discrete random variable, things are a little easier to consider at first because there's not infinitely many possibilities, so it makes it a lot easier to think about. Like the number of students on your committee. There could have been none or 1 or 2 or 3. That's a discrete random variable. Okay. So we are going to focus on discrete random variables and some of the properties of those. All right. So I mentioned before, but number of siblings per student, that would be a discrete random variable because if I'm just going to randomly pick one of you, like pick your name out of a hat, and then I'm going to ask you how many siblings you have. Well, I don't know in advance what number you're going to give me, but what types of numbers do you think are most likely? 1, 2, 3, 4. What types of numbers are not as likely? 50 is probably pretty unlikely. 10, not as likely, right? So I've done this sometimes in classes. I just had some data from one class that I just pulled apart. And so I'm just going to use the data I already did instead of pulling ours just for the sake of time. But this was what one of my classes came back as. Okay, so I just put them into a frequency table, and then you can see in the class I talked to, they had anywhere between 0 and 6 siblings. Actually, nobody had 5 siblings in that particular class, but this is what it looked like. Okay, and you can see the most likely responses were what? 1 and 2 siblings. And if you were to turn this into a histogram or something, it would be kind of what? Sort of skewed to the right a little bit, Most of us are kind of piled up down around, 0 to 4 siblings. And then, some people have 6 or 7 or 10 or 13. It happens. It's just not that common. Okay. Now, when we were first talking about tables, I was telling you, frequency tables are interesting, but normally what we like to do is we like to look at percentages or relative frequencies. So how do you turn a frequency table into a relative frequency table? Like if I didn't want the counts and I just wanted to look at percentages or proportions, what do you do with all these numbers?
You have to divide them. Right?
Yeah, you divide it by the total. Okay, so like here, we could turn that in. So like here, this right here, we could take 3 and divide it by, how many siblings are here? 10, 19, 13, 15. What is it? Did I do that wrong? I'm off by a 10. 16, 26. Yeah. I don't know why I missed a 10 there. But yes, the idea is basically, I did it for you because we're not necessarily, I know you know how to do this. So I'm just kind of showing you, just as a reminder. So we could take all those frequencies and turn them into relative frequencies. So like here, that means about 11.5% of the students in that class had no siblings. And almost 35% of the people in that class had 2 siblings. 4% of the class, which just happened to be one person, but that was 4% of the class, had no siblings. Okay, or 6, so, yeah? All right, so relative frequency is just a measure of proportion. But when you table into a relative frequency distribution, this is kind of like when we saw the probability table with like the different religions or whatever. You can basically treat those proportions like probabilities, because essentially what those percentages tell us is it tells us, like, if I was just to pick one person from this class, those percentages are telling me how likely I am to see someone with those results. Like there's a 0% chance I'm going to see someone with 5 siblings. There's like a 4% chance I'll pull someone with 6 siblings, right? So the proportions can be thought of as probabilities, basically. All right? Okay. So then what we do is we call these tables, these are what we call probability distributions. All right. Because what they do is they show every possible outcome. So these are all my possibilities, and then these are how likely they are to occur. And so that's what defines what we call probability distribution. So that's the definition. I already have these ones filled in, but I don't remember why. I think I recorded this one somewhere. I don't remember why I have it already filled in, but there you go. All possible outcomes and their probability of occurring. So there's 2 things that a probability distribution always tells you. It says it's a way of telling you everything that could happen, and along with that, how likely they are to occur. And so in a discrete random variable, it's not too hard, because if you have a discrete, I'll abbreviate it RV, but I mean random variable there, then that's not too hard to deal with, because there's typically a finite number of possibilities. It's like you exhaust it eventually. Like there's not infinitely many number of siblings that people can have. Somebody in the world has the maximum number of siblings, and we could table them. So. Anyways, when we get to continuous data, it's more complicated because there's infinitely many possibilities, but we'll deal with that later. All right. So then typically for random variables, we typically give them capital letters, just like events, because events are kind of like random variables because they're dictated by probability. So discrete random variables, we give it capital X. So if we define X to be the number of siblings of a randomly selected student in that class, then the probability distribution, we would typically write it like this. So it's like, instead of writing like relative frequency here and the title here, it would just be X, okay, what is X? Oh, it's the number of siblings. All possibilities, P of X, boom, all of these. Okay, does that kind of make sense? Yeah? Everybody okay so far? You with me? And notice what's true about all of the probabilities. They're all between, right? That's one property of probabilities that we learned. And then also one that we talked about a little bit before when we first introduced probabilities. What do you notice? If you add up all these probabilities, what do you think is going to happen? Yeah, the sum of the probabilities should add up to 1 in any probability distribution. And of course, that's up to a rounding error. So you could try adding those. I don't actually know if those ones come out to exactly 1. They probably come out to like 0.99999 or 1.0001 or something. But that's because these were all rounded when we divided by 26. So it's possible that your rounding may end up with that 10,000ths off, just a little bit, but they should add up to basically 1. And these two conditions right here, these are the properties of what we call valid discrete probability distribution. So it has to be true. So in a probability distribution, every probability has to be between 0 and 1. We already knew that. But also, if you add up all the probabilities, they better add up to 1. If they don't add up to 1, you have a problem. It means that you're missing some outcomes or you calculated some probabilities incorrectly or something. They can't add up to more than 1. All right? Did anybody check those? Did they actually add up to 1? Nobody actually checked them. I don't really, it doesn't matter. I'm pretty sure they do. Yeah. Well, you can look at the first column. 4, that's 8, 16. Oh, these ones might add up to 1 exactly. Because the first, but anyways. All right. So far, so good? All right. So basically, I can give you a probability distribution, and then you can know ahead of time what types of things you should expect to happen. So I should know when I go to sample this class, I know for a fact I'm not going to get a student with 5. I'm not going to get a student with any more than 6. This is not very likely. These things are very likely. And in the long run, I'll observe those probabilities. If I kept resampling that class over and over and over, eventually I'd achieve those probabilities. All right. So one thing we looked at back when we were talking about data is that we looked at measures of center and spread. Right. So what happens is that in a lot of cases, you may not actually. This right here, this is a summary, right? This is a summary of data. Yeah? And when we learned back in whatever module 2 I think it was or something, when we learned how to calculate means and standard deviations, we did it with the raw data, like the actual counts. Like I'd have a whole bunch of numbers and I'd add them all up and divide by a certain number, or I'd plug all the numbers in my calculator and then it'd spit out. Okay, but here, I didn't give you the, well, I did originally, but like if you just have summary data like this, I don't have that original data to go from. And so with discrete random variables, you can still calculate the means and standard deviations, but you're just going to have to use maybe a formulaic approach. It's kind of like probability. If you don't have the raw data, you can't calculate the mean and standard deviation from scratch, but you might be able to still retrieve that information. Okay, so that's what I want to look. That's the first thing we'll look at, is how to calculate means and standard deviations. Because there should be some average number of siblings in that class, right? Like the number should exist. What is it, just from looking at the table? What do you think? It's probably around 2-ish, somewhere in that range, right? Just from looking at the table. But there is a mean for those 26 students. So if it exists, we should be able to calculate it. That's the idea. So here's the idea. The idea is like we can think, you don't have to write all this down. I'm just going to show you how why the formula works. But if you look back at the original data I gave you before we turned them into probabilities or proportions, you could actually take that and you could use it to reconstruct the data, right? Because from the frequency table, you could get back to the values. This is like what my original data would have looked like if it was in order. Because 3 people had no siblings, 7 people had 1 sibling, 9 people had 2, and so on. Yeah? Okay, so that's what my original data would look like if I were to go back to like my original stuff. Then from there, well, how do you calculate a mean? Right? How do you calculate a mean from a bunch of numbers? You just add them up and divide by however many there were, right? So you could do it. Doesn't really. It comes out. You were right. It is about 2. If you do for this data set, it's 1.96. So you could add up all that data and you could divide by 26, and then you'd get some number, and that's fine. And you could do the standard deviation. I did it with a computing formula. You could pull it straight off of your calculator too, right? If you wanted to do this in your calculator, you just dump all those numbers in list 1, and then you'd hit, 1 var stats or whatever, boom, boom, and it'd spit out those exact same numbers. Okay. So anyways, so the average number of siblings there is about 2, which seems pretty normal. Now, what you can do, notice though is, all right, so when you look back at the mean formula, how did we reconstruct that original data? Like, we got it from the frequency table, right? Because 3 people had no siblings, so you can think of that as like 3 times 0. And 7 people had 1 sibling, so you can think of 7 times 1, right? And 9 people had 2, and 4 people had 3, 2 people had 4. Nobody had 5, and 1 person had 6. So you could write it as the sum of 26 different numbers, or you could just write it like that from the frequency table. But with an algebra, if you have like the sum in the numerator and a common denominator, you can just split that apart, right? So rather than adding them all up and dividing by 26, I could divide this by 26 and then divide that by 26, as long as I divided every single term by 26, and then add them up, right? That's true? Mm-hmm. That's not like breaking any rules of algebra or math or whatever, okay? But then if you notice, so like if I divide this by 26 and this by 26, I get these numbers, but these numbers should look kind of familiar because those numbers are exactly the numbers that we calculated to get the probabilities, like the relative frequencies. Like when we turned our table into probabilities, you know, from like raw counts to probabilities, well, how did we get the probability of no siblings? We took 3 divided by 26, right? And how did we calculate the probability of having 1 sibling? There was 7 out of 26, and then we turned it into decimal form. Okay? And same here, 9 out of 26, we turned it into decimal form. And so it looks like if you have a table, if you have a probability distribution, like the one we saw, then it looks like, because if you think back, it was like, you know, the probability of no siblings was 0.1154. And the probability of 1 sibling was 0.2692, and so on. So it looks like to calculate an average for, if you just have a table, what can you do? It looks like you can just do what? So look at the numbers there. Right? And what was the probability of 2 siblings? This one was that, right? Right, and so on. But if you compare this line to the original table, it looks like if you want to calculate the average of a discrete random variable, it looks like you just do what? So it's 0 times what? And what is that number?
0.
That's the probability of 0, right? And it's 1 times what number? The probability of 1. And it's 2 times what number? The probability of 2 occurring. And it turns out that's true. You can, if you have a probability distribution, you can just take each outcome times its probability and add them up. So you don't have to have the raw data. You can just say, okay, I'll take 0 times 0.1154. That one's just going to be 0. And 1 times its probability. And then I can take 2 times its probability. And then I can take 3 times its probability. And 4 times its probability. You know, boom, boom. 5 is useless, it's 0. And I can take 6 times its probability. And then we can just take those numbers and sum them all up. And then if we do that, what are you going to get? You're going to get the right answer. You're going to get the same mean. So you don't need the raw data. You can just take the summary data and you can actually calculate the average of a discrete random variable by taking each outcome times its probability, adding them all up. Okay, so this is the formula. Okay, so it's like if you have a discrete random variable with a whole bunch of outcomes and some probabilities associated with it, you know, right? You don't have to worry about the original data set or anything. All you have to do is you take the sum of each outcome, that's the x part, times its probability. Of occurring. and that's the P of X. Okay, so that's just the formula, is just a fancy way of saying that. So. All right. It might sound, look, the formula may look complicated. It's not complicated. So we'll do an example. Okay? I kind of gave you, I kind of showed you why it works. You can do something similar for standard deviation. I'm not going to do that. I'm just going to give you the formula. So this is just the formula. And I'll show you how to work it. So, right, this mean right here, okay, this is the mean that you would have calculated. Okay, and then what does sigma stand for? Standard deviation. Now you notice I have some subscripts here, right? And that's because the subscript, so mu x, what that is that's the mean of the random variable x. Because you could have more than one random variable that you're observing. Like I could have, like it could be mu y. Like you might be observing something else. So mean of the random variable y. So it's just a subscript. It just keeps. It's just like telling you what variable you should be working with. Okay. But we're just talking about like if you have a random variable x, it's called capital X, like number of siblings, then that's how you calculate the standard deviation. Yep. So I'll show you how to use the formula, and then hopefully you'll just take my word for it that that's actually is the formula. But the point is the standard deviation. You have to understand that like there's always a standard deviation in a data set because you can tell me the average number of siblings, but that's only part of the information because I also want to know the standard deviation to figure out how variable the data is. Because two classes could both have the same average, but then they could look very different, right? Like your class and my online class could have the same exam averages, but that doesn't necessarily mean the scores were distributed the same. Okay? And that's why the standard deviation is always a number that we want to be able to access. Okay. All right, so let me show you how this formula works. So here's another example. Okay, so this is the distribution of the number of textbooks that students had to buy, and this was just a sample from a class. The students I talked to had to buy anywhere from none to 5 textbooks, and this was the probability distribution. I left one missing intentionally because what does that number have to be?
Just sum one.
Right, because what you can do is, first off, you just look at all the probabilities that exist. Well, how much probability have we already accounted for? What does that add up to be?
91.
Is it 91?
Yeah.
So if you add all of those together, I've already taken up 91%. So what does this number have to be?
0.09.
Yeah. Right? So you just add up everything else, and then it's just whatever's left over to get it up to 100%. So that has to be 9%. Okay. All right. So now you can see the distribution. The most common outcome was 3 textbooks, but most people were in the 1 to 3, 1 to 4 textbook range. None wasn't as common, 5 wasn't as common. Yeah, but that's the distribution. So then we could calculate the mean and the standard deviation. So like there's got to be some average number of textbooks, right, that people purchase. Well, we don't have the original data, but we don't need it. Okay, so if we call x, then the mean, it's going to be each outcome. So we're going to take 0 times this probability, plus 1 times its probability, plus 2 times its probability, plus 3 times its probability, and then do that for each outcome. All right. And there is no shortcut, really, on your calculator. You just have to do it. But it's not that hard. All you're doing is multiplying a few numbers and then adding up together. This is 0, that's 0.17, this is 0.42. I don't know what it comes out to be, but if a few of you will try that in your calculator for me real quick, then let's see what that comes out to be. 2.6? 2.6? Seems right. 2.6 textbooks, right? And this is an average, right? So on average, students were buying, just over almost 3 textbooks on average. An average doesn't have to be a number that you can actually observe in the data set, right? That's all. It's just an average. That's all it is. So that's the average number of textbooks. Now, if we want to do the standard deviation, so that's just telling me the mean. It's not necessarily telling me how spread out things are, although you can kind of look at the table and get a decent idea of how things are spread out. But if we wanted to calculate the standard deviation, then the formula says we need to take the square root of the sum of the x squares times their probability minus the mean squared, I believe. Wasn't that the formula? Yeah, mean squared. So this number right here, we already know. We just got that. So there's going to be something, that's going to be 2.6 squared. But what we need to do is we need to go get this sum. And so, well, what's the difference between this sum and the one we just calculated? There's not much difference, but there's a little bit of difference. See, for the mean, we just took each outcome times its probability. So for the standard deviation, we just have to square each outcome before we multiply it by its probability. So it would be like 0 squared times its probability plus 1 squared times its probability plus 2 squared. So the sum looks very similar, except for the outcomes get squared before you multiply them by the probability. Okay, so that's the only difference. So like this will become, 0 and 1 don't change, but this will be 4, this will be 9, this will be 16, that'll be 25. So you're squaring each outcome. Then you multiply by its probability, and then what does that come out to be? Any takers on that one? It'll be bigger, I know that.
$8.42.
8.42 going once. Anybody get something different or same? 8.4, not 8.42? 8.42?
Yeah, I'm going with 8.42.
I would like to, but I like to get confirmation on that. I trust you, but
It's a lot of.
it's good to get
Yeah.
multiple data points
It's easy
before
to
you
put
make a
that.
decision.
Put it in a calculator.
Yes. Anybody get something the same or different?
I hate how you have to, once you replace the number, when you copy the equation down, then you have to,
Insert?
you have to retype everything after you insert a number.
Yeah, it's really, well, you can do an insert, but then it's obnoxious. And I can never remember if the inserts go before or after the place where you tell it to insert.
I wish you could scroll down and see the whole.
It's by the delete button. Or it's like second delete. I don't know. We really only have one person?
Second.
What'd you get? All right, perfect. All right. So that is the sum, but that's actually not the answer. That's only partial. That's only part of the answer. The formula says we need to take that sum and then subtract the mean squared before we take the square root. So that 8.42 is that first value that we're going to plug in. So now we need to take 2.6 squared, which I don't know what that comes out to be. What is it? 2.6 times 2.6? 6.76. Okay. And then if you do 8.42 minus 6.76, that gives you what? 1.66?
Yes.
And then you take the square root of that, and what does that come out to be? Maybe around the 2 decimal places or something, I don't know. Or 1 decimal place, doesn't really matter. Square root of 1.6? 1.2, 1.3, somewhere in that range? I don't know.
1.2884.
So we'll go like 1.29 or something. And so that's the standard deviation. Okay? Well, I mean, it's relative. There's harder things you could do.
I just think about time constraints and tests.
Yeah, I mean this is probably this is a 5 minute problem at least, to calculate that. Mostly the standard deviation. So we cover the standard deviation just because the standard deviation is always good, interesting to know, and we're going to see that later on. Standard deviations, there's tons of applications, and they're going to be really important. The mean actually is a little more useful in discrete random variables because one thing, the mean is sometimes called the expected value of a random variable. And like last week, I talked about giving you the option to like gamble, and we decided that it matters a lot what the payouts are. And the reason it matters a lot is because the payout affects the expected value of a bet. And so tomorrow, we'll finish this module tomorrow, but we'll talk about expected values. And really, it's just another name for average. But anyways, we'll do that tomorrow, okay? So that's a good place to leave off.
Two questions. So I just got your message this morning. So what were you trying to say is, if that's my lowest grade, we would just drop it? And
It gets dropped automatically.
But since it was like more of an error from my computer, if I get like another really low grade.
Well, you can just take it.
Okay.
No, that's okay. You can just take it.
Is